time we're going to be looking at more series convergence tests. So let's look at just one example to start, a normal classic example. So let's look at the sum that's going to go from, it's going to go from I equals 1 all the way to infinity. And it's going to be the sum of this expression. In the numerator, we're going to have an n plus 1. And in the denominator, we're going to have a 2n plus 1. So that's how our expression is going to look like. Now this sum, we want to see whether or not when it goes to infinity, is it diverges or converges. So this is actually kind of straightforward, because if we plug in infinity just directly off the bat, we notice that in the numerator, we're going to have infinity plus 1. And then in the denominator, we're going to have 2 times infinity plus 1. Now recall when we're working with infinities, this plus 1 is going to be really small compared to the infinity on the denominator and the infinity in the numerator. Honestly, it's let's just neglect it. So if we think about it like that, we're going to have really infinity divided by 2 times infinity. Now, if you said the answer is half here, you'd be wrong, because once again, the difference between infinity and 2 times infinity, it's essentially the same thing. Unless you have infinity squared, then you'd get something different. But here we see that, okay, it's just essentially infinity divided by infinity, which means you're going to get something like 1. Now, because you get something like 1, this test tells us that if you get something 1 or higher, we don't know if it converges or not. If you get something smaller, we do know that it converges. Therefore, we can say that this series diverges. Okay, let's move on to our next example. Our next example is going to build off of something we learned last time. It's going to go from I equals 1, and it's going to go into infinity, and it's going to be on 1 divided by 4 times n squared. Now, this is going to be something called the limit comparison test. So we're going to actually have a comparison between this and another expression that we looked at in the past. So if you remember in a previous episode, we noticed that if you take the sum of this series, it converges. So it's just some finite value. Now, if you notice this series, each term is just going to be a quarter of whatever term is in this series. That means the sum of this series, whatever it is, it converges, it's going to be 1/4 of a finite amount. And that's also going to be a finite amount, which means we can confidently say this series converges as well. So just comparing the series that you have to series that you already know how they end up, you can make a lot of progress. Okay, finally, we're going to take a look at one final series. Now, this series is going to have, of course, sum from I to infinity of, and we're going to look at 2 to the power of n in the numerator, and in the denominator, we're going to have n times 3 to the power of n. Okay, so to start, what we're going to do is we're actually going to compare each consecutive term. And we're going to say, okay, is the next term greater or smaller than the previous term? If the next term is greater than the previous term, we know that it's going to increase as time goes on. We know that eventually that the series is never going to converge. It's going to go more and more and more. However, if each term is smaller than the term before, we know eventually it's going to go to 0 and it's actually going to converge. So for that, let's take the next term. So the next term is going to be 2 to the power of n plus 1, and it's going to be over parentheses n plus 1 times 3n. Now here we're going to multiply this by a new fraction, and this new fraction is going to be we're actually going to divide it by the old fraction, but I'm putting it as multiplication as the reciprocal. So then let's have the original. So 3 to the power of n. And down here, we can have 2 to the power of n. Okay, simplifying this, we see that, okay, this top part over here and this bottom part over here, we know that if you just divide 2 to the power n from both of them, we're just going to have a 2 in this numerator. And similarly, over here, we're going to have n plus 1 times, well, let's divide both by 3 to the power of n. So now you have just an n over here, and you have a 1 over here, because we divided both of them by the 3 to the power of n and 2 to the power of n, just crossing over. Now, one thing to note is where are we going? We're going to infinity, right? So once again, we can state, okay, there's no real difference between infinity plus 1 over here in this denominator and infinity in here. So we can cancel both of those. It's just I'd like to add in that over here, we have an n plus 1 because of the nature of this is the next term. So we're just going to also multiply this by 3. So if we multiply it by 3, then we're going to have to multiply it to fractions that look like this, but the n's don't necessarily matter. So let's remove both the n's and n plus 1. So we should get a fraction that looks somewhat like this. Remember, let's move that n. So we have 2/3 times 1. That means we get 2/3. Now, does that mean that this series, eventually, the sum of this whole series is equal to 2/3? No, actually, the sum of the series is equal to about 0.69-ish. But the reason that we get 2/3 is you have to remember what we're looking for here. We now know that each term is going to be 2/3 its previous term. But like, where does it start? And exactly, we have some more factors to consider if we want to actually find the sum of this sequence. However, we can assert that it does converge. Thank you for listening to this segment of series tests, and I hope you learned something today.